molecular polarity. This is when a molecule has regions of partial positive and partial negative charge. And these regions are separated from each other in such a way that the molecule essentially has a positive end and a negative end. And that molecular polarity is expressed with an arrow like this that has a plus sign on the positive end, and the arrow points toward the negative end, and this is called the dipole moment. There are two conditions that a molecule must meet in order to be polar. One is that the molecule must have polar bonds with a difference in electronegativity greater than 0.4. So, CH bonds are not polar, but NH bonds are. CO bonds are polar. Remember the trend in electronegativity. It increases as you go up and to the right on the periodic table. But polar bonds alone are not enough. In order to be polar, the molecule also has to have a lack of symmetry. A lack of symmetry can either be achieved through the peripheral atoms being mismatched or through having lone pairs on the central atom, where the electron geometry does not match the molecular shape. But the best way to determine molecular polarity is through drawing the Lewis structure. From the Lewis structure, you get the steric number, which gives you the electron geometry. And once you have that electron geometry, you also know the number of lone pairs and peripheral atoms. And combining those pieces of information gives you the molecular shape. Let's do an example. Let's determine the molecular polarity in sulfur dioxide. First, we count the valence electrons. One sulfur contributes 6, 2 oxygens contribute 12. 6 plus 12 is 18 electrons. Next is the skeleton. Both sulfur and oxygen have the same number of unpaired electrons, 2. But sulfur has a lower electronegativity, so sulfur will be the central. So there is our skeleton. So, our skeleton contains 2 single bonds for a total of 4 electrons, which we subtract, and we have 14 electrons left over. 2, 4, 6, 8, 10, 12, 14. Finally, we apply the octet rule. Each of the oxygens has 3 lone pairs and 1 bonding pair. 4 times 2 is 8. So both of the oxygens have a complete octet. The sulfur, however, has 1 lone pair and 2 bonding pairs, only 6 electrons. That means we need to share a lone pair. And so sharing one of the lone pairs from the oxygen on the right, I can now see that sulfur has 8, and the oxygen also still has 8. So this is a good Lewis structure. So now that we've got the Lewis structure, we determine the electron geometry based on the steric number. There are 1, 2, 3 electron domains, so the steric number equals 3, which means our electron geometry is trigonal planar. So let's redraw our Lewis structure with a trigonal planar electron geometry showing 120-degree bond angles. So now we've got 120-degree bond angles because the electron geometry is trigonal planar. If we didn't have that lone pair, then the bond angle would be 180 degrees. Now we're going to use vector addition to show the molecular polarity. So our molecular shape is bent, with that bond angle being 120 degrees. Sulfur is less electronegative than oxygen, so these green arrows represent our bond dipoles. Now, when you add vectors, you take the tip of the first one and add it to the tail of the second one, and then you connect the tail of the first one to the tip of the second one, and that vector that's produced is your overall vector. In this case, now look over here. I've cut and paste vector A. Now I've cut and paste vector B, and what I'm going to do is line them up so that the tail of B touches the tip of A, like so. And the sum of those two vectors goes from the tail of A here to the tip of B here. We'll call it C. So in vector addition, A plus B equals C. So in this case, dipole vector C is the molecular dipole, the sum of the bond dipoles. And the SO2 molecule, since it contains polar bonds and the electron geometry does not match the molecular shape, that is to say, the electron geometry trigonal planar is different from the molecular shape, bent, therefore the molecular dipole is not zero, and we have a polar molecule. This means that you have a partial positive charge on the sulfur and partial negative charges on the oxygens. Time for some exercises. Try determining the molecular polarity for COS and CH3Cl. Pause the video while you work, then unpause to see if your results are correct. So you'll find that both the electron geometry and the molecular shape of COS is linear. But then you'll also see that oxygen and sulfur are not the same. So we have mismatched peripheral atoms and therefore a lack of symmetry. This means that if the bonds are polar, the molecule is polar. Looking up the electronegativities, oxygen is 3.5. Both carbon and sulfur are 2.5. That means the CO bond is polar and the CS bond is nonpolar. And so the molecular dipole is the CO bond dipole. And therefore this is a polar molecule with a delta plus on the right hand side and a delta minus on the oxygen. Because the molecular dipole is greater than 0, COS is considered a polar molecule. Now we'll do CH3Cl. Once again, pause the video while you work. Unpause it when you're done to check your answer. A quick word about this diagram. This is using perspective to try and communicate three-dimensional data. Atoms that are at the end of a wedge-shaped bond are coming toward you, and atoms at the end of a dash-shaped bond are going away from you. So here is our tetrahedron. Our electronegativities are 3.0, 2.5, and 2.1. That means the CH bonds are all nonpolar because their difference in electronegativity is 0.4. The CCl bond, however, is polar. Since there are no other dipoles, we have a molecular dipole that's greater than 0, and therefore a polar molecule. And this means that the chlorine has a partial negative charge, And the other end of the molecule with the carbon and the hydrogens has partial positive charge.